Hello everyone, my name is Praveen Suresh Samgir. I am from Pune. I have done my master's degree in physics from Ferguson College in 2015. I have 3 years of experience in teaching field and about 6 months of experience in software field. And today I am going to discuss the topic semiconductor physics. Okay, so let's start. We have not too much time. So let's start for semiconductor physics. So now, if you see around us, we can see so many things like wood and whiteboard and bulbs and electronic devices and so many things. Okay, but they are not same. Okay, they are different from each other. So what are the properties? What are the characteristics which are make different from each other? Them. Okay. So some are conducting materials, some are non-conducting materials. Okay, some are insulators, some are semiconductors. So what is the science behind it? Okay, so we'll study this today. If you see in earlier years, like in 1940 or 1960, the computer size was like a one huge bedroom. Okay, but nowadays, if you see our electronic devices, we have very compact devices. Like if you take mobile phones, okay, we have 10 GB RAM and size will be in our one palm. Okay, so if you take tablets or laptops or so many electronic devices, so how this possible, means how we reduce this size and the efficiency increase. So what is the science behind it? So this happens because of this semiconductor physics. Okay, so very interesting topic we are going to discuss today. Increase your curiosity. What is the basic factors? What are the physical concepts behind this which make our science? And so let's discuss. So today we are going to discuss these 4-5 types, like electronic configuration, then energy band, then band gap, then classification of materials and semiconductor types. Okay, so let's start. If I say word atom, so what image comes in your mind? So some kind of this of structure will imagine. Okay, so in here we'll have a nucleus in center, and in that nucleus we have protons and electrons, and electrons are revolving around it. Okay, around it. So this is how atoms looks like. And so today we are interested in electrons. Okay, so we'll discuss all about electrons. Okay, so if I told you, if I tell you, give me your address, or I want to find your address, so what will tell me? So it will tell me something like your flat number, your taluka number, your gully number, okay, or your district something, or that's that type of things you will tell me. So if I want to know how many number of electrons in first orbit or how many number in second orbit, okay, so how we will find? So for that we have electronic configuration. Okay, so by using electronic configuration we can find how many number of electrons are there. For that we made electronic configuration. So suppose we took first orbit, so how many number of electrons will be there? So for that we have formula 2n square. By using this formula we can find how many number of electrons are there. So n is the orbit number, and we'll put that orbit number in that 2n square formula, 2n square, and we'll get the number of electrons in particular orbit. Okay, so for electronic configuration we have another subchase like S shell, P shell, D shell. Okay, so for S shell we will have 2 electrons. Okay, pair of electrons. In P shell we have 6 electrons, and they are configuring pairs, like suppose this first pair, second pair and third pair. Okay, and in D shell we will have 10 electrons. Okay, again they are in pair form. Suppose we took the example of silicon, so we'll have a configuration like 1s square, 2s square, 2p6, 3s square, 3p2. So that's how we distribute the electrons in electronic configuration form. Okay, so here I have written some energy levels. Suppose E1, E2, E3. For first shell we will have 2 electrons. For 2s, 2p6, total will be 8 electrons. Okay, so here in n is equal to orbit number 3. For energy level 3 we will have 3s, 3p, 3d. Again for in S shell there will be 2 electrons, for P 6 electrons, for D 10 electrons, and total will be 18 electrons. So that's how we define or we configure the electrons. Okay, and we will get the exact electrons address we can say. Okay, so next topic will be energy band. So So energy band, suppose we have one atom having only one electron, suppose hydrogen atom. Okay, so for first orbit we have one energy level. Suppose we have two atoms of hydrogen and we will have the same energy level, so we will get the two separate energy levels. Suppose these two atoms are far from each other, then we will get the two energy levels but in same energy levels. Okay, if we close these two atoms, so we will have the two energy levels but they are split. Means initially suppose we have a x energy level, okay, x value, and suppose we close them to each other, so this energy level will be split and we will get the two energy levels. Okay, suppose we have three atoms and we close together, so we will get the three energy levels. Means single energy level is split into three energy levels. Okay, and suppose we have a n number of atoms having the same energy, the single energy will split into n energy states. Okay, and here you can see we are getting a band. Okay, here band is forming, so that's how energy band is formed. Okay, and for that we have two type of bands. One is a valence band and another is a conduction band. So we have a valence band and another one we have a conduction band. So what is the valence band and what is the conduction band? So valence band is a band where uppermost totally filled energy level called as a valence band, and conduction band is lowermost empty energy band called as a conduction band. Okay, so here all electrons are filled, means all energy states are completely filled, and here energy states are there but they are empty, called as a conduction band. And this portion is very important, called as a band gap. Okay, our next concept is band gap. So what is band gap? The region, forbidden region, where there will be no, means no electrons, means empty states. Okay, means there will be a restriction of electrons to move from there. Okay, that is the forbidden gap or band gap. So this is a very important topic for semiconductor. Means this band gap plays very important role in semiconductor physics. Okay, keep in mind this band gap makes material different from each other. So this is the important concept, band gap. So we represent as energy level Eg, energy gap. Okay, so valence band, conduction band, Eg. So on this band gap we will have three types, means conducting material, semiconducting material and insulator. So we'll discuss this topic. Okay, so our next topic is classification of materials. So you can see here I have drawn some diagrams. So according to band gap, our materials are differentiated from each other, means some are insulators, some are conductors, some are semiconductors. So how it's possible? So band gap is a major role behind it. So you can see here we have valence band here and we have conduction band. So you can see the gap between these. Okay, so this gap is about greater than 5 electrons, means these are the huge gap, means no electrons will come from valence band to conduction band. So these are the empty states. Okay, there will be no free electrons, means it will behave like a insulator. कोई भी इलेक्ट्रॉन यहाँ पे जितनी भी एनर्जी स्टेट्स है they are completely filled, और यहाँ पे जो एनर्जी स्टेट्स है they are totally empty. Okay, there will be no electrons, means there are zero chances of flow of electricity. They are behave like an insulator. So for that the energy band gap is greater than 5 electron volts. ये बहुत ही important चीज है, जे में भी पूछा जाता है इस पे MCQs, ध्यान रखना. Okay, so for conductor here valence band and conduction band are overlapping each other. Okay, means energy gap is 0 here, means electrons from valence band can easily flow in conduction band. Okay, they can transit from valence band to conduction band. They are overlapping, means you can see here they are overlapping. Okay, so these are the ions and copper type of material. Okay, so and third one is a semiconductor, means what? At T is equal to 0 Kelvin it will behave like a insulator, means conduction band will be empty. Okay, and the valence band will be completely filled. Okay, no free electrons will be here. And as we rise the temperature, some electrons from valence band will go to the conduction band. Okay, and we will get the free electrons. So as electron come from here to here, we will get here some empty states called as a hole. Okay, we will get a hole, and here we will get a electron. So we can call as a electron hole pair formation. Okay, so that's how semiconductor works. Okay, so at some temperature it will behave like a conductor, at room temperature it will behave like an insulator. Means it shows both properties. So this is the very important topic, silicon for semiconductors. So semiconductors are silicon and germanium are the semiconductor. For silicon we have a 1.1 electron volt energy gap, and for germanium we will have a 0.7 electron volt energy gap. Okay, so according to this we are interested in semiconductor materials. Okay, so for semiconductor materials there are some types again. For semiconductor we have a intrinsic semiconductor and extrinsic semiconductor. And again in extrinsic we have P type and N type. Intrinsic means pure semiconductors, means the material which have no doping elements, means they are purely formed, means they are in their output there will be 4 electrons. Okay, there will be no doping, they are pure. Okay, for extrinsic means dope materials, dope elements, means we are doping or adding extra elements in that, so we can get the we can achieve the result which we want. Suppose we add a pentavalent elements, we will get a N type of materials. Okay, or characteristics, or if you add trivalent impurities, you will get the P type of material. Okay, so that's how semiconductor materials distribute in different forms. Okay, so we'll stop here. Thank you so much.